All right, let's start. Any questions from Tuesday? Any thoughts on what we have seen about how to reason about approximations? We've seen now two lectures on approximations, and in both cases, we've seen this basic paradigm of trying to figure out, imagine what the optimal solution might be doing. So figure out that it must be constrained in certain ways based on the input, and then somehow cleverly design your algorithm to take advantage of those things that the optimal is forced to do. Right? So that's kind of the very high level, somewhat vague rubric for how to think about approximations. We've seen approximations for problems that are actually not that hard to solve, but that requires a certain amount of resources, and you can save the amount of resources used by doing something approximate. We've seen problems where we actually don't know how to solve a problem efficiently at all, and it might be hard to do it. And so that's our only hope is to be able to approximate to something. That was last lecture. Are there any other questions about so far what we've seen? We're going to see more of this today. Okay, so let's continue on. One of the problems, of course, when designing an approximation strategy is the same problem you have with designing any algorithm for any problem. You don't know up front whether what you're going to be able to achieve is even possible. Right? So it's always helpful to say, okay, I have this problem, let me see if I can design something that works in linear time. Maybe it won't work, but it helps to have that focus because it says, okay, if I want something to work in linear time, there are only certain techniques I'm allowed to use. I can't use some kind of brute force enumeration. I can't do certain things. So it constrains the space of possible attacks you might bring to the problem, and it helps to focus. And after a while, you try it for a bit, you fail. And you say, well, I don't know, maybe I'm just not smart enough to come up with it, maybe it can't be done. And you don't really know for sure, right? So there's always a dilemma. You never know for sure whether, if you had just thought harder, you could have come up with something versus not. And so I want to walk through one such problem today where, it's not a priori clear whether it's possible to do something or not. And we have to sort of probe at this problem a little bit, see where its weaknesses are, and try to find a way of attacking the problem. Okay? And the problem we're going to look at today is what is called the traveling salesperson problem. You probably have all heard of this one, but let me define it. Oops, sorry. That was terrible. The input to such a problem is essentially just a collection of distances. So it's, in fact, you can think of it as a distance matrix. Right? So I have the input consists of n, we'll call them locations, but they're really just things, just entities. You can think of them as numbers 1 through n, if you wish. Doesn't really matter. Because all that really does matter is how far apart these things are from each other. So you're given some distance function. Let's call this, I don't know, b. The positive reals. Really, it'll be the positive integers. And the goal is to find an ordering of the locations 1 through n. So let's call it v1, v2, vn, such that if I add up the distance, if I now think of going from location 1 to location 2 to location 3 up to location n, so such that the sum distance vi to vi plus 1, I equal to 1 to n minus 1 is so this is the complete definition of the problem. You've never heard it before, this is all you need to know. Good to go. And of course the physical model of what this is doing is that you have, say, this person who has to cover a neighborhood, or who has to, or maybe, you know, someone wants to visit every single baseball stadium in this country. I know of someone who decided it would be a good way to spend their sabbatical. So I don't think I told their university that. So, and so you have all these locations, and they have distances between them. And so you have a choice now, right? You can go through them in any order you want. And of course there are n factorial different orders. What I want to find is the best ordering, measured by this notion of best, where the amount of travel time it takes me, or travel distance is as small as possible. Okay. There are slight variations. Sometimes you want to loop back to the beginning, so then I would add an extra n and then put a mod. You know, but they're basically the same problem. Yes?
Are you allowed to cross the same location twice to get to another place?
Sure you can. You can do whatever you want. It doesn't... Actually, no, you visit each location once. It doesn't really help to repeat locations, because you're going to... If you visit a location twice...
Well, I was thinking like there are two
well,
cities.
okay, this brings up a subtlety that we'll get into in a bit. But for now, let's assume you visit each location exactly once. Okay. All right. So this is a problem. We may not know too much about it. And we want to find a path. And that's often how, this is often how a problem eventually will get to someone who thinks about algorithms for a living. It's been modeled in some way. Maybe these locations were actually, so here's a somewhat esoteric version of this. I mean, all you can imagine the actual traveling salesperson, but this is a paper I wrote some years ago where this ended up being this problem, but where it started off was with laying out stuff on disk. So you have a bunch of, essentially, let's see how to think about this. You have a bunch of views. So you're walking through a large scene with many polygons in it. Okay, and so it's such a huge scene that you actually can't store all the information in memory. So you have all your different scene viewpoints are sitting on disk. And you have some kind of walkthrough you're doing through the disk, through the scene. And you want to somehow organize your information on disk in such a way that when you have to get the next scene from the current scene, the amount of information you have to pull in is as little as possible. And there's a way to model this as some kind of distance between scenes. So you want to reorder your scenes in some form so that the distance between any two adjacent scenes that you might pull through in your walkthrough is as small as possible. And you end up with some version of the traveling salesman. Okay. So there are many ways in which you can come across this problem. And of course, a lot of the work in modeling is figuring out how to abstract the problem in this form. But let's say you do have this. And now you want to know, okay, what do I know about this problem? What can I solve? And so if you look very quickly, you will find that this problem is known to be NP-hard. I want to prove it here. It's one of the, for very simple problems, it's very easy to prove NP-hard just by reduction from 3-SAT. So that much we know. So we're unlikely to get an exact solution to the problem. We don't see any good reason why we can. And so that n factorial solution starts looking very attractive. If n is less than 5. Of course, if n gets to be much larger than 5, then that n factorial solution does not look so attractive anymore. And so you have to come up with other ideas. And so you've taken the class like this, say, oh, okay, there must be some kind of approximation algorithm I could come up with. And like any other algorithm, you would think, okay, what are the tools at my disposal? I know things like divide and conquer, I know things like greedy algorithms, I might do some time. These are all standard tools I have at my disposal. I could easily apply them to this problem and try to get some solution that looks plausible. Okay? And then once I get one, I can try to prove that it has some reasonable properties. And that's pretty much how we might think about it. So what I want to do is just give you 5 minutes or so, just to get a feel for the problem. So I want you to, so each of you, or maybe groups of at most 2 if you like, so think about this problem and start thinking about how you might try to go about attacking it. I don't need to know whether it's, right now, whether it's a good solution or not. I don't need to know whether, you can make any claims of correctness of optimality of any kind, because it's going to be hard to do that. I just want you to let your mind float a bit as to what might be plausible. And I would like you to give me your reason as to why it might be plausible to think about this. Okay, so I'll give you 5 minutes, just go ahead and chat and think. And you can talk, it's not a secret thing.
Okay. They call them traveling salesmen because they're assuming that it's a salesman.
If you're already familiar with this problem and know some of the solutions that exist, try to pretend like you did, because it's always helpful to get to that point yourself.
And I forgot. I've heard of the problem. If there was solutions, I totally forgot. I don't understand. So the key is that, let's say they call it traveling salesman because he was traveling around the country. He would have to go to all the different cities, but only go to one. So yeah, you wouldn't want to go boom. I mean, obviously, but you want to somehow go like that. So once we get to like that, probably would get short. What I could think of is probably what is nearest to you, go to that place. And after that, what is nearest to you? That seems the most obvious, but I think you could probably create a graph where that would work. So,
I mean, we can just go to, for example, if I'm going here, then if this is smaller, so I will go here, probably this is not.
let me give you an example. Let's say that there was one over here, and you started here. You say go to the nearest one, nearest one. You end up over here, and then all of a sudden you jump there. So probably the best would be to jump there first, and then here. So that's why that algorithm, it wouldn't work on this graph. So
Yeah, that would work. That is one kind of mistake.
you know, when you look at it, when you read the site, visual site, it kind of right, you can kind of see how you would do it. But obviously a computer can't do it. So my thought is, why can't we try to simulate how we do it? Right? Because if we see it, we can kind of see what the pattern would be. Well, the computer could do it because they could try every single option. But if it is
I think there's a button for
you can say, well,
We can't say if it is like lots of minus.
true.
Lots of minus, then we are not.
You're a good point. That's a good point. That's a good point.
I don't know if
only the end part of the slide. Yeah.
But let's say that you had some points over here. Obviously, you don't want to go boom. So that going to the closest is let's have some reasonableness.
because you try to finish the class.
Right. So like in a cluster, you would want to get a cluster to. So yeah, clustering is good.
Okay,
I like the fact that
All right.
yeah, clustering is a good issue.
bring me your pearls. Who would like to volunteer? Go.
I mean, find the nearest point, which is begin with the nearest point, go like that continuously, then
Find the
find the nearest point of.
to where?
I mean, if I am in one position
Yeah,
and I can access 3 points,
yeah.
find this least distance on closest. Okay.
Okay. And then keep going.
Yeah, and keep going. And visit it only once. Make sure you mark it as well.
Sure. Okay, very good. Any other thoughts? Yeah?
You could take your set and instead of being the nearest neighbor, you could try to cluster it and then solve smaller
So say it again. So you take a set. You do what? You cluster it.
cluster points that are close by.
Okay, cluster points. So you have clusters now, and then
And then you solve a correspondingly smaller traveling salesperson problem.
on each cluster,
Yes.
and then
Recenter.
well, now you have little tours in each set.
Yes.
So now what do you do? How do you hook them all up into some gigantic set?
So the larger idea was that you would somehow have a knowledge of the diameter of your set.
Yeah.
So I don't know if it's easy to find the longest path between 2 points, but you
Okay.
would set one. Once you find that, you'd have one as your start and one as your stop.
So let me just pull this up. So I understand this first part. So you create a bunch of clusters, and now you have little paths in each of them, right? Is that correct?
Yeah.
And now you want to kind of glue them together.
Yes.
What would you do then? So now what do you do?
You could cluster the clusters.
You could cluster the clusters, so you would group these together.
No, I mean,
So if the first one is clusters of 5, then you have clusters of 5. So then you'll solve the problem.
That's fine. And as a divide and conquer strategy, this is great. But what you're telling me is a divide part. You're not telling me the merge part. I need to know how you combine things together. I
Then
understand
you combine 5 clusters together.
how.
You
each
treat
cluster
them
as a
each
single
as
point.
one node.
And then what do? You run a TSP
You
from
do
here
a
to here?
traveling salesman between the 5.
Between the 5. Okay, so you try to connect them. And you in other words, but you have to use this tour that you've built, otherwise it'll be a waste.
Yeah.
You someone say, okay, I want to get a tour from here, from this endpoint to one of these endpoints,
Right.
and something like that. Okay, good. So let's call this divide into clusters and then merge. Okay. Any other thoughts? Any other ideas? Yeah.
So what would happen if we treat this like a graph and then got rid of all of and sorted all the edges and got rid of the most expensive ones first, so long as they won't like break a cycle or
Disconnect the graph or something.
yes.
Well, you can assume the graph is fully connected because I've given you distances between all pairs. So the graph is a clean. Okay, good. So now you delete the expensive edges. You have some idea of expensive, okay? And you remove expensive stuff. Then what do you do?
So the idea is that you reduce the number of edges down to where you have some sort of minimal. And the way you reduce edges is a little
So the idea is to somehow remove the edges from the graph in some disciplined way so that what you have left is now an easy problem to solve. What would be an easy instance of the traveling salesperson problem?
how do you mean?
So you said I want to remove edges so what I get left is kind of easy to work with. It doesn't have too many edges in it, right? So
I would say the easiest problem would just be consider just 2 points and the shortest path between those 2 points.
would be a tour, right? So if you removed enough stuff so you had only 2 vertices left, that would be easy. But let's say we don't want to disconnect the graph, so we still want to have all n vertices. In that case, and you're just removing edges, what would be an easy,
a linear one, connecting all the points.
like a path, for example? So suppose you could remove enough edges so you're left with a path. Now it's good. Now you solve your problem in some sense, right? So the third strategy is something like this. Remove expensive edges till graph becomes easy, like a pot. Okay, very good. We have 3 ideas that are all, I think, very nice ideas for how to attack this problem, and actually have people tried using these strategies. So this is good. What else? Any other idea?
Treat it like an optimization problem.
Spell
Create
out.
just create a particular path, and then you
Sorry, kid.
you pick a path at random, for instance. It's like
Pick a path at random. Okay.
and then define a cost function.
Yeah.
based- And then iterate on that using an algorithm
Gradient descent,
simulating.
stochastic gradient descent, something. Okay.
Yeah.
So good. Another idea for this is to
Pretty horrible way to do it, but
no. we are currently in a judgment-free zone. It's the only way to do this kind of work, be judgment-free. So, essentially, create a seed path and do some kind of gradient descent or optimization from there. Okay, this is good. Yes?
Okay, like when we're removing expensive edges, what if we find the cheapest, the shortest edge in the whole graph, add that to our solution, and then the next shortest, and the next shortest, and the next.
It's going to work from both directions. And riffing off the idea of we don't want expensive edges, also add in, but we want the short edges.
Yeah.
Okay, so you kind of work from both sides. Okay, so let me actually add that as a variant here. Okay, good, very good. This is great. I mean, these are exactly the right kinds of things that you'd start off with when you take a problem like this and start trying to play with them. Any other thoughts? Anything that are sort of distinct from all these ideas that we want to throw out there? Yeah.
Well, I don't have it clear in my head. I was wondering if we could maybe start with the minimum spanning tree,
Okay.
and then basically, I guess for any node that has or for any location that has a degree greater than. So if I'm only.
So let me stop you saying why minimum spanning tree?
Well, if we were, well, the minimum spanning tree will get us, the minimum connected graph.
Okay.
So I was thinking if there was some way we could take that and then maybe.
So you're riffing again off these ideas of get some kind of small graph that's easy, and
Yeah.
that's in some sense the minimum connected graph you can get. Is that your idea? Okay. So let's write this down. So let's first write down what you said. It's not fully So start with the MST and then do what? So yeah, tell me what you're thinking.
It would be something like, so I remove all the edges that are on the MST.
Yeah.
For any location that has a degree greater than 1, it was going to have, it'd have to be something like remove edges so that every node has a degree of 1, and then somehow randomly add other edges too.
Yeah. So because the MST itself has nodes of degree more than 1, and you're worried about that because now I can't get a nice loop.
Yeah.
Is that the problem? So you're saying if my MST happened to be this, I'd be happy. But if the MST happens to be this, I don't know what to do now. Right? And so you have to find some way of doing it. Okay, good. Very good. Yeah?
So is it possible to sort of solve the problem by brute force, but like start with a smaller subproblem and sort of cache that result?
Okay.
Add another node.
So another idea is, and this is again a very well established technique for dealing with these kinds of hard problems, is solve smaller sub-problems and cache the results. This is all making me very, very happy, and I'll tell you why. I'm going to go back and relabel these ideas with something, and you're going to see how wonderful all your ideas were. This is a classic greedy strategy. It's a very natural strategy. It's definitely something you should think of doing. It's a greedy algorithm. And greedy algorithms are great to get a sort of sense of what's going on with the problem. Okay? This one, the second one, is a classic divide and conquer. Again, a very sort of standard way to attack a problem. And again, I remember I told you on day one, what you want from this class are tools, right? You may not be the most, you may not ever work in algorithms and be an expert. You want tools. These are all tools, and these are tools you should apply, and I'm glad you're applying them. So divide and conquer, we'll write this down here. This is a other kind of recursive strategy which has a similar flavor to the previous one, but is doing it in a different way. We're saying, instead of just doing divide and conquer, we're going to be very careful about how we sort of strip ourselves down to some simpler problem that we can solve. Do it in some intelligent way by removing these expensive edges or by adding short edges, and then fine. So I'm going to call it a general recursive idea. So general recursion. Okay, which is again a very nice way of thinking about these problems. This is a classic, let's put this into the framework of some larger optimization paradigm and solve it there. And we'll see that as well later on in the class. So I'll call this optimization. This is, for example, very popular when you're doing machine learning, that you sort of take your problem and you cast it in some kind of generic optimization framework, because now there are tools you can apply that will just go and crunch through. And that's also good. The MST idea is a variant on the recursion idea. It's saying, let me find small subproblems that are easy and work my way up from there in some form. So it's a recursion, but again a flavor of recursion, where you're saying, you know, start with easy and work up. And this last one, where you solve smaller subproblems and catch the results, is of course dynamic programming. Another sort of standard technique that people use to solve these kinds of problems. So in one problem, we've basically been able to come up with reasonable lines of attack by applying all the tools that you've all seen in some form, sometimes with some variance based on the actual problem you're dealing with. And this is exactly the right way to sort of think about these problems. You know, and we don't know if any of them are going to work. We're not even at that point yet. That's not the issue right now. The issue is to come up with some idea. Okay, good. The next thing to do once you have an idea you like, you create this beautiful idea, you sort of think about it a little bit, the next thing to do is to break it. Because most times your first idea is not going to work. If it works, great, but it's not going to. And it's good to know where it breaks, because then that tells you where the second idea is going to come from. Yes, you had a question?
Can I use MST with graph matching? Can I use MST with graph matching?
You can do whatever you like, but what I'd like to know is what's your intuition?
Like remove the set of edges without a common,
So we talked about MST as why MST somehow is interesting here. Can you tell me about matchings? Why do you think a matching is interesting here?
Because you can remove the edges without who have common vertices, so that I can just find out only the mean and
Because matchings are also things that have only degree 1. Is that your idea?
Yes.
So you don't have too much extra degree flexibility. Maybe. So let me add that to the MST idea, and I'll put a question mark on matchings. Okay. All right. So now let's take one of these ideas. I don't want to go through all of them, but we'll just take one. I'll take the easy one, the greedy one. Let's try to break it. Can we find where it fails to do what we want? And okay, yeah, I'll just stop there. So anyone would like to venture where the greedy strategy might break? Then the way to do this is to come up with a simple example. Any simple example will do it. Yeah, Victor.
If we have some sort of diamond of a graph.
So let me draw a diamond. Okay, so let me draw a diamond here.
So one on top, two in the middle, one on the bottom.
Pardon me?
One on the top, two in the middle, and then one on the bottom. And if we're starting at the bottom and going up, the left one could be something like 10.
So I should remind you though that in my input to the traveling salesperson problem, we have distances for all pairs of nodes. So when you're drawing a graph, you're welcome to draw one, but really you should be thinking about this graph. If you're thinking about measuring distances, does that change your answer in any way? You can put whatever numbers you want, that's up to you, but you should still think of all possible edges. You can make those numbers in the middle really big if you want, I don't care. Did I just derail your example?
Maybe, I don't know.
Well, why don't you continue? Let's continue with this.
Well, let's continue. And so, I guess, so 10 on the left, some really large number in the middle.
So 10 on the two left edges?
10 on the very left.
Okay, let me label them.
Okay, yeah, thanks. So DB10, DC1, and then CA is
You can change it later. So just make it. I don't mind.
let's see this.
So what you're trying to do is break the greedy example, which is start somewhere, take your nearest neighbor, and keep going. So you can join the fun if you have an idea of it.
Yeah, sorry. I started thinking about the next one. I didn't realize.
So if the point is to visit every node once, at the shortest path, you might miss a node depending on it.
Right, but I think the idea was take the nearest neighbor if it hasn't been visited. If it has been visited, take the next nearest neighbor. If that's been visited, take the next nearest neighbor. Yeah?
If you have like 2 cluster of points connected by a bridge.
Oh, so wait, are we giving up on this example? Okay, fine, that's fine, that's okay. So 2 clusters of points.
Yeah, they're connected by a bridge.
Bridge, wait.
You move from one cluster to the cluster, but you miss some points in the first cluster. You have to go back.
But in the how will the greedy strategy make that happen?
So if you have a straight line that are the closest points from this cluster to that cluster,
Yeah,
but there are some points in this cluster that are not
that close, they're far away.
Yeah.
Okay, so my cluster command looks like this.
Yes. There.
So it's easy to go across, but it's hard to go down.
Yeah.
So I'll go back and forth a lot.
Yeah.
Why is that a bad thing?
So your distance will go.
It will, but maybe that's okay. Maybe it's so far to go down. Oh, I see. Possibly. I would have liked something a bit more concrete, but I think you're on the right track. I see how this could be massaged maybe to lead to an example. But so for example, you might have something here, and something here. Then you have something short here, something here, something here, something here. Is that what you're saying? So I start here, I go here. Now what do? By the algorithm, I'm going to go here. Then I'm going to go here.
You have to go back all this.
Okay, so I go back maybe here. Yeah. Would there have been? But I've only gone across, twice. You're saying it might have been better to go like this, and like this, like this, maybe. It's possible. We'd have to check the numbers to see, but it's possible. Yes.
Can I try to fix the first?
Feel free.
Can you make CD 0?
CD 0.
And the 2 middle edges.
I'm not going to make it 0 because I don't like zeros. So I'm just making that some very small number. Yeah.
Make it 2 middle ones, so A, B, and B, C.
Big. Okay, fine. I'll make them big. Okay.
AC is 10. And AB is like 1,000. So what happens here is, if you're starting at D, you walk to C, and then you don't go to B because that has an edge of infinity, so you go to A. And then you're sort of stuck now because you have to go to B, and you can't go back to D because that's even more expensive, so you go to B over this edge of 1,000. But it's more efficient to, for example, start at D, go to B, come back, and then go to CA.
But you can't come back. I mean, you have to visit every vertex exactly once.
Okay, so you can start at D, go to D, C.
Sorry, start at where? B? Oh, okay. So the correct tour is start at B, go to D, go to C, and go to A. So that's 10 plus epsilon plus 10. Right. But
If you start
we'll
with
give him
B,
a chance to defend his idea. Yes?
I mean, it all depends on where you start with greedy A's.
So can you modify your greedy algorithm?
I mean, if you, oh, okay.
Yes?
I can actually modify it. It doesn't have to go it one way. You can go at the front or at the back. So for this problem, if you meant A, then you can go from the back to expand to go from D to B. And then you will find the shortest in this problem. But actually I can fix the first, like if you have 2, like for A to B, B to D, D to C, C to A is 2.
You can fix that, so it's 2?
Yeah, like for the other is 2. And then if you start from the point and say B to C is 1,
Yeah.
and then A to D is infinity. So then if you start from
Okay, okay, I think I see your example. Let me just draw the example. So to answer your question, his greedy algorithm can be fixed very easily by saying, run the greedy algorithm from every point of the input and see the best answer you get. That will neutralize your counterexample. Because your counterexample relies on not knowing where to start. Since there are only n starting points, if we're in the world of polynomial time algorithms, it is acceptable to say, let's try all of them and see the best one we get. That would neutralize that particular counterexample. But now we're going to see, we're hopefully going to see another counterexample where that will not matter. So let's see what that one looks like. Okay? Yes?
In the context of real world applications, traveling salesman problem, the starting point is usually fixed and not something that we can achieve.
Right. But if the starting point is fixed, the problem has also changed. Because the problem is now saying, starting at this location, find the best tour you can find. Which is a different problem. A slightly different problem. It will still have the same complexity as this problem, but after you've removed the first element. So now from the first, I can decide where to go next. And then again, we're back to the same situation. So the idea that your first point is fixed doesn't fundamentally change the complexity of the problem. It just makes your problem of size n minus 1, effectively. Because what you could do is take your remove the starting point, optimal cycle in what's left, and then from the first node, find the cheapest one to jump to. And you would have solved that problem. So they are essentially the same problem. Does that make sense? So if that constraint can be folded in without fundamentally changing the complexity of what we're dealing with. Okay? Alright, good. But it's a good observation, and it's good to think about what would happen in that case. And then we can say, okay, look, well, that case can be reduced to this case, so let's not figure out this problem. So let's go to this example here. Okay, so here's the example. I'm going to draw this again. A, B, C, D. I think you said this would be 1 and this infinity. Okay, explain, tell me what's going to happen.
No matter where you choose from, then you always, either you go to, when you go to B or C, you're going to choose the 1. And the only way you're going to choose what thing.
So okay, so the correct tour here, the best tour here has cost 8 is what you're saying. Right, so for example, A, B, C, D has got 6. Right?
Yeah.
And that's oh sorry, A, B, D, C, sorry, has cost 6. And now what you're saying is that if you apply the greedy algorithm, and suppose you start at B, then your first move is going to be to go to C. And then you're stuck because you can go to either A or D. And now you have to go to the other one and your cost is going to be infinite. Is that what your argument is? Suppose I start at A though. Then I could go back the other way around. And then as long as I get to B at the end, I don't have a problem.
So you would go A, C, and then C, B, and then B, B.
Right, so I could go, for example, A, C, D, and B, and that would be fine too.
No, if you are in C, you would go to B anyway.
Oh, I would go to B. Okay. So right. So if once I touch the BC set, I'm in trouble, and I have to touch the BC set to get across to D.
Well, I'm saying A,
No, I
C,
mean,
B, D.
You can.
Yeah, AC,
Well, it's even
is
better.
fine.
Oh, it's even
Yeah,
better.
that's 5.
Oh,
So our greedy algorithm found one that we didn't intuitively know.
yeah, that's great. Algorithms are fun. So the greedy algorithm lives to fight another day. At this point, you might think, okay, fine. This is actually, so now the pendulum is gone. So you've gone from, okay, yay, I have an idea. Okay, B, let me break the idea. Okay, I tried breaking it, it didn't break. Okay, maybe it actually is a good idea. Now let's see if I can prove that's a good idea. And you could try to think about how do I prove that this greedy algorithm actually gives me a reasonable answer. Can you at least prove that it's not optimal?
What if B and D was infinite, D and C were infinite, and A and B were 10?
Okay, hold on. Tell me again.
BD is infinite.
So BD is infinite.
CD is infinite. AD is 10.
Wait, if BD are infinite and CD are infinite, your tour cost is infinite.
No, AD is 10.
Oh, sorry. You got me there. Okay.
BC is 1.
No, sorry.
And those other two are 2.
Okay, what now? What's the optimal cost here?
So then BC will always be in the path.
BC will always be in the path because
because you're always taking the shortest edge.
Wait, are we starting from B?
I guess that one works too. That one works.
Well, B cannot be anywhere except at the end, otherwise we're in trouble.
Right.
Because if we get into D, then we can't get out. So D has to be at the end. So therefore B and C have to be in the middle somewhere. Right? Either one of the two of them has to be second or first. And so now what happens?
Doesn't A have to be second or last? So
You can start with D and then also.
Okay, so I start with B, what happens? So I start with B, I go to C.
So, yeah.
And then I go to A, and then I go to D. That's 13. Isn't that good?
Yeah, that's it.
Darn it! Foiled again. Maybe we have discovered a solution to this problem, which is NP quality. Yeah, we have it. Sorry to burst your bubble, we have not. But unless we can come up with a way this algorithm breaks, we're not going to make much progress on this problem. We have to be able to break it, otherwise, we have no way to say that it's, not optimal or optimal.
It's like running the all pair shortest path.
Pardon me?
This is like running the all pair shortest path.
Is it? It's greedy. All per shortest path's not greedy.
I mean, like it's much worse like the same.
Yes, but okay, it's similar. I'm not sure I'd agree with that statement entirely, but it has certain nuances that look like that. Yes. So what do you do now? It's possible that we need a more complicated example. This example is not somewhat complicated enough. The example that we had about that seems more promising, where you have a bunch of things that are here, but you get distracted by zipping across so much that you're unable to. But we need to construct. Yes.
Just create a path with like a path of say length 5.
Yeah.
Where you have 5 nodes, each
Yeah.
with weight 1 between them, and then that's a node on the other end of the path with a weight of say 6. Or say 4, or
Yeah.
3, just something slightly larger than 1.
Yeah.
Then it'll keep walking along that path. Oh, and then at the very end you create like a loop back to the...
Okay, you need to walk me through this. I'm not...
Or wait, never mind, forget about that.
Okay.
Because I think you could mislead it. You create a bunch of low weight paths to kind of send it off.
That's the right idea.
Yeah.
That's the right idea.
No, I mean, but as you said, if you are starting with n different points and trying one time, you will obviously find a proper answer. So
Really?
even if you are...
Oh, that's a very bold claim you make. You're basically saying that greedy is correct?
No. I mean, if for this example, if you are trying to lure it towards the other end,
So here's the thing, you need someone to make your input symmetric, in the sense that it doesn't matter where you start from. You somehow have to figure that out in your input. I mean, your input has to be symmetric enough that wherever you start from, it's not going to change things. These inputs are kind of symmetric, but they're failing for other reasons. Like they're taking care of the starting point problem, but they're failing for other reasons. So I'm going to let you think about that for a little bit. It's a fun little exercise to sort of ponder how you break an algorithm. So it's a good practice to learn how to break algorithms, because that tells you where they go. But I want to burst your bubble a little bit. I'm going to prove to you that this strategy is not going to work. In fact, I'm going to prove to you that all of the strategy you described I mean, if you think of, if your definition of horrible is that they give a 10, it's worse than that. If your definition of 100 approximation strategies, that's the sad thing I'm going to show you. But I'll let you be happy. So here's what we're going to show. We're going to show that so it's a relative approximation. if there is any function g of n, which could be a constant, could be log n, could be anything. If there's any function that allows you to solve that such that you can design an approximation to solve a TSP, that means your solution will be the optimal solution times g of n. For any g of n, then you solve p equal n. This is, needless to say, very depressing news. Yes?
That doesn't disprove our algorithms, right? That just says if we were to find an algorithm, we would prove equal to p.
Good point. I am underestimating the collective capabilities of this class by saying that. This is correct. You could have, in fact, proved equal to n. It's just unlikely. I will only go that far. I will not discourage your No, it's a good point. No, he's correct. All I can say is that it's highly unlikely that any of those things are going to work. I cannot say they won't work. Well, to be more technical about this, there is a way in which I can say they actually will not work because it's a long story. Right? You don't want me to get into this now. So not only do we not know how to prove whether p is equal to np, very helpfully people have shown that none of these proof techniques you can come up with can be used to show that p is not equal to np or equal to np or anything like that. They're just inadmissible. So there's lots of ways of trying to prove p not equal to np or equal to np that are not allowed because they won't work. You can sort of just say at a high level that they just cannot be made to work. And these would fall into that category, but separate discussion. Okay. So in other words, what I'm going to show to you is that the problem of approximating the TSP to a factor of g of n is itself an NP-complete problem. Because that's what the definition of NP-complete is. Or an NP-hard problem. The definition of NP. Okay? And that's both very disappointing and very bizarre, but it also tells you about what the limits of what you can do with approximations themselves. And in order to show this, and this is where some of your counterexamples start becoming interesting, is that I'm going to exploit some properties of the input that you've been implicitly trying to exploit in your examples as well. And I'm going to show you exactly how to make that help you to build a counterexample. Example of a gap result, right? So here's what, let me give you the proof first, and I'll explain to you what the proof is really saying, because it says something much more than just proof is problem. So how many of you have heard of the Hamiltonian path problem? Some of you? Okay, let me define the Hamiltonian path problem. So we'll call it Ham because I'm hungry. Let's say G is a graph again. Okay, and so the question is, this is a decision problem, so it's a 0-1 answer. Question: is there a path visiting each vertex exactly once? Okay. Now, if I give you a yes.
Alright, so there are limitations on G then?
Any bomb.
So I mean, like for example, you said earlier that.
Let's say any polynomial if you want. It doesn't. I mean, there's some technical reasons why G of n should be a polynomial. But
I mean, like if G of n is n factorial, then you solve it exactly.
Well,
you said earlier that TSP can be solved in factorial time.
time. That doesn't mean the approximation ratio is n factorial. Right? I mean, the actual values could be very large, right?
So G of n is not time bound.
No.
It's the approximation.
Yes. Yes. And let's say it's polynomial for now. Otherwise, as you get this, actually, technically, this should be a polynomial because of other technical reasons.
And presumably, meaning the algorithm is.
Yes. If there is an yeah, when I say an algorithm, if there's so if there's a otherwise, yeah, then we prove it. So do you understand the problem of Hamiltonian cycle? So there are two kinds of cycles. There's an Eulerian cycle, there's a Hamiltonian cycle, right? The Eulerian cycle problem is easy. If you know some basic graph theory, you can tell if a graph admits an Eulerian cycle or not. A cycle that visits every edge exactly once. But a Hamiltonian cycle problem is a lot harder when you want to visit every vertex exactly once. So for example, if I give you a path, then of course that's a Hamiltonian path because it's a path. If I give you a tree, and there's at least one node of degree 3 in the tree, so it's not a path, then now you have a problem, right? Because you may not be able to read something in one node. So you clearly, for any given graph, it either does admit such a path or it doesn't. The question is, which one of the two cases is it for any given graph I can give. And this problem is known to be NP-complete. Okay? And what I'm going to show you is that if I could solve the traveling salesperson problem to any kind of approximation, I would solve the Hamiltonian path problem. And here's my reduction. Just like any Gardner's reduction. So I want to take an instance of the Hamiltonian path and make an instance of traveling salesperson. So it's a very simple reduction. I'm going to take my graph. Let's say the distance of u comma v is equal to 1 if u v belongs to the set, and du comma v is equal to let me think for a second what I want to put here. Let me put something like k for now. And assume k is much more than n. Okay? So I've taken a graph which is the input to a Hamiltonian path problem, and I've constructed a distance matrix which is the input to a traveling salesperson problem. Okay? Okay. Now let's look at the cases here. So case 1, G has a Hamiltonian path. What would be the cost of the optimal traveling salesperson tour if G in fact has a Hamiltonian path?
Some of all exist.
N minus 1.
It'll be n minus 1 because there's a path, you just find it, right? So the cost is less than equal to n minus 1. It's actually equal to n minus 1. Suppose G does not have a Hamiltonian path. What is the cost? What can you say about the cost of the best traveling salesperson? Yeah, Daniel?
I guess it's greater than n minus 1.
But can you say anything more?
There's got to be k in there somewhere at least.
Okay, so its cost is going to be, it has to have n minus 1 edges in it. At least one of them must be k, because you have to use one invalid edge. So the cost is going to be right? Yes? So in other words, by constructing this reduction from Hamiltonian path to TSP, what we are saying is that we have created this kind of blow up. And let me draw this as a picture for you. What we've done is we've taken, so let's say that we encode the Hamiltonian path problem as 0 if it doesn't have it, as a 1 if it does have it. So we have a 0 and we have a 1 case, right? And the TSP, we have a n minus 2 plus k versus n minus 1. And I drew this in this way because what we have done is gone from a gap of 1 to a much larger gap. If we think of this gap as a kind of ratio, this ratio is n minus 1 plus k minus 1 divided by n minus 1. I just took out a 1 to make it easy, which is equal to 1 plus k minus 1 over n minus 1. And remember I said that k is much bigger than n. So basically this ratio is governed by this ratio k over n. Why did I do this? Because here's what I want to say. Imagine that you had an approximation algorithm for TSP that guaranteed some kind of ratio, let's say a k over n approximation for the problem. So let's say that g of n was something like k divided by n. I haven't chosen k yet, so it's some number. Think of k as like n squared. So just say g of n was k over n. And I gave it this instance I got from the Hamiltonian path problem. Because the algorithm claims to be a k over n approximation, it can tell the difference between that case and this case. It has to be able to. Because if the true answer is there, the answer the algorithm returns can be not much more than that value times k over n, which is going to be less than this. And so it will know the difference. So if there was an approximation algorithm with this approximation ratio, then I could tell the difference between these two cases, and I could tell if the graph had a Hamiltonian path or not. But that problem is NP complete. Therefore, this problem is NP complete. But I didn't tell you what k was. All I know is that I'm labeling the edge value, which is why k needs to be nothing that's too big. It can't be, it has to be at least some, well, a k can be actually have an exponential value because I can write down polynomial number of bits. So actually, I can make this. Because I can choose k to be whatever I want now. I can make k arbitrarily large. This still holds. As long as I label the infinite edges with some very, very large number, essentially infinity, but some practical version of infinity, I can say that any approximation guarantee up to that point will solve the Hamiltonian path problem for me. Which is why the TSP cannot be approximated to any approximation factor. Unless p is equal to n. Yes?
So we can't approximate it with some fixed k above it. However, we can approximate it just like times 2 of the best possible solution.
We can?
Yes.
No, we can't. I just proved you can't.
Well, so this is for some constant k. If it's dependent on the size of n, then it's still possible.
No, I'm going to make k to be n squared.
Yes.
So then I can't do a better than n factor approximation. I'll make k 2 to the n. Then I can't get a better than 2 to the n approximation. I can make k whatever I want. K doesn't have to be a constant. I just put k as a placeholder that I don't want to think about it. But I can make k anything I want it to be. Yes?
How do we add a set of vertices to the Hamiltonian?
Pardon me?
I mean, how do we add vertices to the Hamiltonian?
I didn't add anything. I just said take the graph corresponding to the Hamiltonian path problem and construct the distance matrix that TSP expects us in this manner. So it's a reduction, right? I'd say, okay, I have my graph, I apply that. I don't know if the graph has a path, I don't need to know. I'm just constructing that blind reduction. And it automatically makes sure that a solution gives me one value and the not solution gives me another value. Like any other NP-hardness reduction. No? You don't believe me? Not convinced. So I'm not adding vertices, remember. The input to the traveling salesperson problem is a matrix. I told you, just n locations. And the only information you have about them is a distance matrix describing how far apart things are. There's no graph, no. All I have to do is produce a distance matrix, I just did that. So I have a valid input to the problem.
But I still need to find the Hamiltonian path.
No, what I'm saying is that if I could get a good approximation to the TSP, I would get the Hamiltonian path. Because the TSP would give me a path with a certain cost. I'd say, oh, this cost is in the right range, therefore it's a real path, let me take those edges, that's my Hamiltonian path. Or the TSP would say, this is my path, oh, it's in the wrong range, there is no Hamiltonian path. So I can use the answer I get from TSP to produce an answer, one way or the other, for the Hamiltonian path. That's what I'm going to do. Right? Yes?
What if we had an approximation algorithm that had an approximation value,
A ratio.
but with a certain percentage of getting that value, a certain probability of getting that value?
This reduction does not apply. If you want to that there is no randomized strategy that has some certain, there are other things you have to do. This reasoning does not apply. But we don't know of any, I don't know of any good examples where, well, I know of one. Okay, but yeah, so there are some cases where randomized strategy can actually do better, yeah. Where deterministic strategy cannot do better. But this doesn't apply here. We're still talking about just a straight up. Yes?
The decision question that we used for the Hamiltonian problem, is that itself the NP-complete problem?
Yes, this is I'm giving you as a fiat, as a sort of given it's known to be NP-complete. You'd have to prove that, but it's known. Yeah, this is one of the original NP-complete problems. Yeah, and that's how you always start. You start with a known problem, you try to reduce it to a problem. So this is what is called a gap sort of reduction. It's giving you it's taking a small gap 0 to 1 and blowing it up into a big gap, which is this, and that's showing you that you cannot do any approximation. So the TSP is hopeless, except it isn't. But in order to do anything better, we have to look more carefully at what the structure of the problem is. What this is saying is that if you know nothing about your problem, you cannot get a good approximation. But let's think for a second at the kind of distance matrices we get from this reduction that are telling us we can't do this. What is it telling us? It's saying basically, so think of a graph that looks like this. This is my graph, and in order to make it into the TSP, I do the same thing. I'll put all 4 edges now to represent the matrix. So I'm going to put a 1 here, a 1 here, a 1 here, a 1 here, an infinity here, some very large number like k, and an infinity here, right? This is my distance matrix. Now, I want you to look at this. Imagine any place in Salt Lake City where you could have distances that look like this. Maybe not infinity, but large numbers. It's saying that if I have to go from A to B to C, it takes me 2 steps. But if I go to AC directly, it takes me infinite steps. And no one-way streets, in case you're going to think about that. Yes?
I was just wondering, are we going to have distance matrices that are positive semi-definite?
Now you're being too clever for me. So since I haven't mentioned the first time, I'm going to say, huh? I mean, I actually know what you're talking about. I'm not going to, let's not, yeah. But we are getting to some important point about these distance matrices. Yes. So we are getting somewhere with that point. Yeah. But you're asking for too much. So yes.
So maybe something like dropping altitude versus going up in altitude. Something that could look like that.
Oh, you'd have a mountain in the middle?
Yeah, like going down would be easy, going up would be very hard.
You could, if you put a big mountain in the middle here, something really, really huge.
Yeah, I guess.
Yeah, that's easier to go around than go up and down it. Yeah, but my problem is not measuring, how good your legs are. It's just looking at the distance. But yes, you could do it that way. The point I want to make is that the distance matrices you result in when you claim that the TSP is hard to solve are very bizarre distance matrices. They don't capture what one would normally think of as a reasonable distance matrix. This is of course a judgment call, right? Your reasonable is my unreasonable and so on. But they don't even capture basic properties that we expect a good distance to satisfy. Namely, if I can go from A to B, and then after that I can go to C, it shouldn't take me any more time to go to C directly. It would be kind of weird if that were to happen. And again, assuming no mountains. There's a name for this property.
Triangle.
It's called the triangle inequality. And it says that, there's a class of distance functions which we'll call distance metrics. Okay? That in addition to other properties have this key property, that taking shortcuts is a good thing. Unless you go through someone's backyard, they shoot you, but that's a different story. But generally speaking, taking shortcuts is a good thing. And if we now say, no, we only want to consider the traveling salesperson problem on distance matrices where shortcuts are a good thing, that whole reduction breaks. We no longer can prove that it's hard to approximate. Because we've looked at the structure of the problem and said, oh, this reduction is very brittle. It requires very bizarre, strange things to happen to the distance function that are not realistic. Okay. So suppose we now require that our distance matrix, in addition to being, having numbers that are positive and that are symmetric, has this property that for yz, dxy plus dyz is greater than or equal to dxc. In other words, shortcuts are cheaper. Then what we get is what is called a distance, not a that means this. Okay? What happens then? It turns out now that TSP is very easy. You can solve it really well, just by observing this one fact. And I will leave you to convince yourself that any normal distance, like walking around on the street, or Euclidean distance, or walking in New York City, and Manhattan distance, is in fact a distance that has this property, that shortcuts are good. The best way to get somewhere is to take a straight line, so on. So this is not an unreasonable assumption. You'd be very hard pressed to come up with a distance function that does not satisfy this. Most reasonable distance functions do. So it's a good assumption. And here is a very simple algorithm. That's, again, you will see this as being very familiar now, based on what we said earlier. Here's the idea. So here's an algorithm. Okay? That's step one. Step two, that means a duplicate. Okay. 3 is construct an Euler tour, and 4th is, I'll explain all these steps in a second. Okay, so again, maybe I should just walk through an example. So the idea is we're going to show is this following. It's a very simple idea. So we talked about how the minimum spanning tree is kind of like, something that might be useful in this regard, because it has this minimum connected flavor to it. There's something we can say that's even more interesting about the MST. So I claim that, so hopefully you all know what a minimum spanning tree is. Basically, it's a tree. Every tree has a cost, the sum of the distances on the edges. The minimum spanning tree is the tree that connects all the vertices that has a minimum total cost. And if you remember from greedy algorithms, there's a very simple greedy algorithm to construct a minimum spanning tree. You sort the edges in increasing order of cost, and keep taking edges as long as you maintain a tree structure. Something creates a cycle, throw it off, and then that's it. It's Kruskal's algorithm. There's also prims, and there's a bunch of other ones. So here's the observation. So the optimal tour is a path, right? A path. This tour is greater than or equal to the cost of the minimum spanning tree. You see why? Because every path is a tree. If I take all paths, which is what I want, it has to be more than the minimum over all trees. So therefore the opt is 1 in. Why is this important? Remember what I said last time. The goal in approximations is to get lower bounds, if you're minimizing, on the optimal solution. Lower bounds that you can work with. We have a lower bound. We know the minimum spanning tree is less than or equal to the optimal solution. The problem, of course, this was true, by the way, even before. The problem was that before, we didn't know how to take this MST and get an actual solution out of it, as was observed, right? The tree itself doesn't give us what we want. There's no way to sort of route around the tree, because you have to visit every vertex only exactly once. But let's draw a tree. So let's say our minimum spanning tree looks like this. You have A, you have B, you have C, you have D, then maybe you have E, F, G. So let's say we took our distance matrix, we construct a minimum spanning tree and it looked like this. And I want to construct a tour on this. What do I do? First observation I'm going to make is, let me duplicate every edge. Okay? Every vertex in this graph, this tree now, has even degree. If I duplicate every edge. The things that were even degree stay even, the things that were odd now become even. A graph in which every edge has even degree has what is called an Euler tour. A cycle that visits every edge exactly once. So Euler's famous result that sort of started the birth of graph theory came from this result back in the 1700s. In fact, if you go to Königsberg, well, the ancient Königsberg, which is now a town in Poland, you can actually get Euler tours. You can pay money and get an Euler tour of all the bridges that he sort of solved. This is my dream to one day go and do this. So go to the actual Euler tour. Yeah, so since you have an Euler tour, you can actually find the path that visits every edge. It's actually not that hard to see what this path will look like. If you start from here, you just go down and do what is called, I always forget, an in-order traversal of a tree. So you go from A, go down to B, go to C, you go back up to B again, go to D, then back up to B again, then E, then F, then E, then G, then E. If you want to go back, then B, and then A. You can verify that you traverse every edge of this doubled tree exactly once. And this is your tour. And now, you use the fact that short-circuiting is a good thing. I had to measure. This is not a valid tour because I'm, repeating visits to things. But it's I can short-circuit. For example, I go from A to B and I go from B to C. I've already seen B before, so I don't have to go there again. So I go straight from C to D. I've seen B before, so I go straight from D to E. I go to F, and I go to G, and I'm done. So my new tour is like this. Okay? Now this is a valid traveling salesperson tour. The question is, what is its cost? It's no good unless we know what its cost is. So observation 1. Its cost is clearly less than this entire cost. Why? Because I was able to short circuit. Right? Instead of going from C to B to D, I went straight to D. By the triangle inequality, I know this can only reduce my cost. I didn't have that before, but I have that now. So the cost of the actual tour, which I'm going to write down in red here, which is going to be A, B, C, D, E, F, G, is less than, so let me go back to here. So let's say this has cost C, this has cost C prime. C prime is less than or equal to C. This much I know, right? By the short-circuiting property. What can I say about the cost of C? I've traversed every edge in my graph, right? How many edges do I have? I've doubled the MST, right? Cost of C. C is equal to twice the MST, right? Okay, so let's put everything together. We know that the MST is less than or equal to oct, right? But we know that the MST is also more than, so we also know that the MST is greater than or equal to C prime divided by 2, right? because C prime less than 2 MST. Yes? So if we string these inequalities together, and I'm going to go to the next page here. So I have C prime less than 2, less than equal to MST, less than equal to opt. Now my lower bound is done, I pull it away. I have my 2 approximation. So you see what the lower bound did for us? It gave us a way to argue about the relationship between our solution and the optimal solution by acting as kind of a catalyst to sort of grease the conversation a bit. So again, going back to the previous argument, because of 2 things, well, because of one fact, the triangle equality, we knew that by short-circuiting a long circuitous path through the tree, we don't increase the cost. Something we could not have said earlier. And as a consequence of that, we are now able to say that our cost is not that bad, because all you do is just double the cost. Yes?
Suppose we have a directed weighted one.
This doesn't work.
Sorry?
This doesn't work. This method only works for undirected graphs. Undirected weighted graphs.
So if we have such a graph, then we can't use it.
You can't use, well, it's harder. This is what is called the asymmetric traveling salesperson problem. The best known bound for that is a factorial log n. It's much worse. It's a different problem altogether. Once you put directions on edges, this whole argument breaks. You need a different set of arguments altogether. Yes?
So if you were a delivery service like FedEx or UPS, I'm assuming you'd do something like this, but you know if like one-way streets or these kinds of things?
One-way streets get to the asymmetric problem, and that's a much harder problem. There are solutions for that as well. And this is the simple version where it's all, everything can go both ways on streets. But you can incorporate that notion. Yeah. Any questions? So basically, so here's the situation as stands, right? So general TSP, no approximation. So it's really hard. Metric TSP, 2 approximation. In fact, and I'll say this, I'll tell you about this, you can get this down to 1.5. If you now allow yourself to say, well, I don't have an arbitrary distance matrix, but what I have is a graph where all edges are of weight 1, but I just have a graph, you can do slightly better. So unweighted. No, sorry. Let me say that again. Yeah, you have an unweighted graph, and the distance between any pair is just the shortest path distance. So, sorry, I didn't say this right. So the distance, you have a weighted graph. No. Okay, you know what? Never mind. I was correct the first time. You have an unweighted graph.
Are you able to revisit vertices?
No, same rule applies. The distance function is generated from the shortest spots on the graph. That's the key. The matrix is even more special. Then you can currently get something like 1.4. I don't know if it's the best thought, but you can get 1.4. And if you're actually in the plane, so you climb plane, you have shortest spots using the L2 distance, you can get, I'll explain what this means next time. You can get an arbitrarily good approximation. Anything you want. So the importance is that, just because a problem might be easy or hard to solve, it doesn't mean the story stops. By adding more structure to the problem, you then are able to pull out more information out of it, and often you can do a lot better. So we stopped here today. I will mention this next time. These are much more complicated, so I won't talk about them. But before we all go, we have a minute or two. Any questions? Yes?
We have taken the triangle inequality using a distance form, but if we talk about real world, we don't have a
Sorry, if you can all, one second, I couldn't hear the last bit.
I'm just saying, we have considered traveling salesman problem. If we apply it to the real world, we are considering triangle inequality, but triangle inequality will not hold in the real world.
It actually does.
But if you talk about India, there are paths like this. going from 1 to 2 distances, like this path will be better than going straight, because there is no straight path, you will be having the curved path.
There's no straight path is the example of the graph, where the distance is the best shortest path. That's actually even easier.
Let's talk about curved path.
That's fine, doesn't matter. You find the best way to get from Delhi to Agra, whichever that way. That's the distance from Delhi to Agra. You can find the distance.
But going by some other way, like I'll go from Delhi to like Gurgaon and then go to Agra.
That might take longer.
But you were talking about the 2 points are.
But there's no actual connection. The connection is virtual.